Given a list of potential side lengths, your task is to find 3 lengths that can form a valid triangle and result in the largest possible perimeter. If no such triangle can be formed, you should return 0. This problem tests your ability to combine geometric rules with efficient search strategies. The challenge is to select 3 distinct side lengths from a given array of positive integers. These 3 lengths, let's call them A, B, and C, must satisfy the triangle inequality theorem. The sum of any 2 sides must be greater than the third side. That is, A plus B must be greater than C, A plus C greater than B, and B plus C greater than A. Among all valid triangles, we need the one with the maximum perimeter. A straightforward but inefficient approach is to iterate through all possible combinations of 3 distinct side lengths. We can use 3 nested loops, picking one side with each loop. For every triplet, we check if it satisfies the triangle inequality. If it does, we calculate its perimeter and update our maximum perimeter found so far. This approach involves checking every single combination, leading to a time complexity of O(n cubed, which is too slow for larger inputs. The space complexity, however, is O(1) as we only use a few variables. The key insight for optimization comes from the triangle inequality itself, especially when combined with sorting. If we sort the array of side lengths in descending order, say A, B, C, where A is the largest, then A plus C will always be greater than B, and B plus C will always be greater than A, because B and C are smaller than A. Therefore, we only need to check one condition. If B plus C is greater than A. If this holds, then A, B, and C form a valid triangle. By sorting the array in descending order, we can iterate from the largest possible sides. The first triplet A, B, C that satisfies B plus C greater than A will give us the largest possible perimeter. Why? Because we're prioritizing the largest sides first. If we find a valid triangle with these large sides, any other valid triangle formed by smaller sides will necessarily have a smaller perimeter. Let's trace this with an example. The input array is 2, 1, 2. First, we sort the array in descending order, so it becomes 2, 2, 1. We start iterating from the first element, which is at index 0. Our first potential triplet consists of the sides at index 0, 1, and 2. These are 2, 2, and 1. We check the condition. Is the side at index 0, which is 2, less than the sum of the sides at index 1 and 2, which are 2 plus 1? Yes, 2 is less than 3. Since the condition is met, we've found our largest perimeter triangle. We calculate the perimeter as 2 plus 2 plus 1, which equals 5, and immediately return it. The final answer for the input array 2, 1, 2 is 5. This is correct because the sides 2, 2, and 1 form a valid triangle with the largest possible perimeter, as 2 is less than 2 plus 1. You'll spot this greedy pattern when a problem asks for an optimal value, like the largest or smallest, and involves elements that can be ordered. If sorting the input allows you to simplify conditions, or make local optimal choices that lead to a global optimum, that's a strong hint for a greedy approach. The time complexity of this optimized solution is O(n log n due to the initial sorting step. The space complexity is O(1), or O(n) if the sorting algorithm uses auxiliary space. Try applying this greedy sorting technique to similar problems. If this explanation helped, hit that like button and subscribe for more efficient algorithm breakdowns.